Hey everybody, hwsteele here. This is going to be a slightly quicker video. I say that, it's probably still going to wind up to be 10 minutes long, but anyway. This video is going to be the second one I'm doing about the law of vibration, but I'm going to go into music and talk a little bit about some mathematics, some ratios in music, because we're going to start using music to help us quantify the law of vibration, at least as we apply it to some markets. And there needs to be some fundamental information given out in this video so that everyone's on the same page, hopefully, when I start looking at the markets with these ideas, concepts, and numbers. Now, this is an octave right here, the do, re, mi, fa, sol, la, ti, do. An octave is named so because it has 8 notes or 7 steps between those 8 notes. And thus that ties the number 7 and 8 together in the octave. And the names of the notes are right here. There's also letter names for them, but we're not going to be talking about that right now. And here we have ratios. These ratios are applied to the number of vibrations per second. So if this do happens to be 100 vibrations per second, then the re is going to be 112.5 vibrations per second. The mi is going to be 125. The fa, 133. And so on, because you take the vibrational rate of the do and then multiply it by these numbers to get these notes. So if you have a vibration of 100 and then multiply it by 1.5, that's going to be the so note. So if we look at the names of these notes, you notice that do and do, obviously it's the same note, it's just 1 octave higher. Anytime you double a vibrational rate, it's the same note, but it's 1 octave higher. If you divide it by 2 instead of multiplying it by 2, it's 1 octave lower. But the so right here, which is the vibrational rate that's right in the middle of these two do's, also has an O in it, in its name. The fa and la are the only 2 notes that have A's in the name, and they're the 1/3 and 2/3 notes. And the mi and ti are the only 2 that have the I in the name, and that's the 1.25 and the 1.87, which at first glance it doesn't really seem, there's no connection right there, but there actually is. And then the re is all by himself right there at 1.125. So we just look at that. That's important, but we're not going to talk about it in this video. The only thing I really wanted to show you is that we're going to be using the natural ratios, not the equal temperament ones. And equal temperament, all that is where the natural ratios are altered just slightly, so the mathematics between changing keys on instruments like, for instance, a piano, where it has a specific tune that cannot be changed easily or at all. I mean, it can be changed, but you have to, you spend a while doing it. When you're playing, you don't change the tune, is what I mean. Having these ratios be slightly off makes the math between changing keys more pleasing to listen to, basically, is what it boils down to. And anyone who knows music understands all of this already. But those of you who don't know music are probably ignorant of it, and it's something that needs to be understood before we can go further. At least the very basics of it. And if you're interested in this and don't know about it, it's very, very easy to research this on the internet, the ratios and names and so forth. So the other thing I wanted to talk about in this video is the fifth, the fourth, and the third, the perfect fifth. The perfect fifth, the name fifth actually comes from the fact that there's 5 tones in it, not including semitones. We're not talking about that in this video. We're just talking about the 8 classic notes, or the 7 classic notes, I should say. But a perfect fifth is 5 notes and 4 steps. So we have 1, 2, 3, 4, 5 notes, but if you start here, it's 1, 2, 3, 4 steps to get there. And the last note's always going to be 1.5 times the vibrational rate of the first note. So if we get a calculator, just an example, and we use mi, which we'll say is 125 if our do is 100 vibrations per second, then the mi is going to be 125, and if we multiply that by 1.5, we get our 187.5, which we start here. So it's step 1, 2, 3, and 4 for our fifth tone. That's 187.5. If we were to start here at 133 and multiply that by 1.5, we would wind up at 199.5, or round it up to the next whole number of 200. So we would start here. This would be 1, 2, 3, 4, and our fifth tone, or fourth step, would have us at 200 vibrations per second. So a perfect fifth, the first note, and then the last note, the separation between those is always going to be 50% value of the first note in vibrations per second. The fourth is 3 steps or 4 notes. Pretty easy, right? 1, 2, 3, 4, or 1, 2, 3 steps. Now let's look at some of the math for that. If we're starting out at 100 and we do 4 tones, 3 steps, we see that the ratio is 1.33. So the final tone is 1.33 times the vibrational rate of the first tone. If we take mi, for instance, 125, multiply it by 1.33, we get 166. So we go 1, 2, 3. We find out that we're right here. If we were to start at, for instance, so, which is 150, multiply it by 1.33, again we'd be at our 199.5, rounded up to 200. Starting here, we go 1, 2, 3 steps, or 4 total tones, and we're at our 200 right there. Okay, so that's the fourth. Now the third, you're probably able to guess what that is. It's 3 notes, right? 2 steps. But because we're not dealing with semitones, we're going to see a bit of an abnormality here. The ratio is 1.25. But if we start, let's say we start at 125 and then multiply it by 1.25, we get 156. Now let's make our 2 steps. We started here, we go 1, 2, and we see that we should, in quotes, be at 1.5, but we're actually at 1.5625. So let's look again, let's look at 133 as an example. Multiply that by our 1.25 ratio. We get 1.667. And we start here and go 1, 2, and here we wind up where we're supposed to be at 1.667. But if we start here at so, which is 1.5, multiply it by 1.25, do we wind up where we're supposed to? Starting here, 1, 2, yep, we sure do. So the question is, why did we have an issue over here and we didn't over here? And the answer to that has to do with the semitones in the octave. And I'm not going to get into that right now. If you want to research that, you can, and you'll be able to answer the question as to why that's happening. But I want to point something out to you. The first is that with a fifth, we have the ratio, the steady ratio of 1.5. A fourth, we have the ratio of 1.33. And the third, we have a ratio of 1.25, but it doesn't always work. Now, that's going to play out later, okay? We're going to be looking at that in more detail later on down the road, so to speak, in future videos. Okay, so, well, look at that. The video's already 10 minutes long. I'm going to go ahead and end it here because I just wanted to get this very basic information out at first. And like I said, if you know about music, you already know all this. If you don't know about music, then you have a basic starting point, a little bit of a foundation where we can take some math and go to the market with it in the next video. This is just the very basic. Like I said, this doesn't involve semitones. It's just the basic octave, 7-step, 8-tone octave here. It gets more involved, definitely, and there is an octave structure. Actually, there are several octave structures that don't really coincide exactly with music, that are deeper also, that we're not going to get to for a while. But anyway, just wanted this information out there so that our next video would make sense to those who don't know music. And that video probably will show up in the beginning of February. So anyway, this is hwsteele, and I will talk to you in the next video.